back to the fourth installment of the AP Easy Chemistry Chapter 16 Precipitation Equilibrium problem set. Let's take a look at problem 53. You're given a lot of information in this particular one as well. You're told that blood can be treated by putting C2O4 2- into it to help keep the calcium ions from interfering with the quality of the blood. You're told that if normally blood has 0.1 milligrams of calcium 2 plus ions per milliliter, and you're dealing with a 250 milliliter sample of blood that's treated with 250 milliliters of 0.160 molar sodium Na2C2O4, you're asked to figure out in the end how much calcium remains after you precipitate out the calcium oxalate. So my first advisement on this one is to calculate your moles of the calcium and your moles of your oxalate. So you take your original given information and find that before you do any precipitation, just in the original solution samples, you have 6.2 times 10 to the negative fourth moles of calcium ions and 0.04 moles of the oxalate. And there's way less calcium, so that's definitely going to be your limiting reactant. Just look at the magnitude of these. If we put them in both scientific notation, the oxalate would be 4 times 10 to the negative second. This one's times 10 to the negative fourth, 100 times smaller. Then I say, all right, write an equation out to kind of express what's really happening here. You've got your solid substance breaking apart into two separate pieces, and you can have a KSP for that. Solubility product of 4 times 10 to the 9th is the looked up value, and the KSP is going to be, since these ions are in a 1-to-1 ratio, the KSP is going to be just calcium ion concentration multiplied by the oxalate ion concentration. You can safely assume that all the calcium is going to react because it's so much smaller. It's the limiting reactant. It's only going to leave you with 0.0394 oxalate unreacted. So then I would go about trying to find what the concentration of the oxalate is by dividing it by the total volume, and you get a 0.0788 molar oxalate solution, and then plug that into the KSP equation and solve for what the calcium would be after you've precipitated out all the original calcium. You're only going to get a small amount of calcium to come back into the solution that redissolves after this solid substance reaches an equilibrium with the substances, the ions in solution. And in the end, you solve out for the calcium Ca2 plus out of this last expression down here, and you can find the concentration is 5 times 10 to the negative 8th molar. Alright, problem 57 is rather involved, so let's take a quick look at it. You're dealing with 25 milliliters of 0.5 molar iron sulfate and 35 milliliters of 0.332 molar barium hydroxide. You're told two different precipitates are formed. You're asked to write a net ionic equation. Here is a quick look at your net ionic equation. You can write it as one giant thing or break it up in two separate pieces. I think the two separate pieces is probably a little easier to see. You're forced to estimate the mass of the precipitates that are formed, so you first calculate the number of moles, so use some dimensional analysis, find your moles, and then you can find what your, since the total volume of the solution is calculatable in the previous part, you can find what your molarities are for these. But it might be easier to just stay in moles for now. So then you determine your limiting reactant. The limiting reactant is the hydroxide in the iron and hydroxide reaction. The limiting reactant in the barium with the sulfate is the barium. So you can figure out how many moles of the product you should actually make from that. And then if you assume that 100% of the product will actually form, considering your limiting reactant, you can get masses of these substances. 1.04 grams of the iron 2 hydroxide and 2.71 grams of the barium sulfate. Alright, now you're also asked to calculate the equilibrium concentrations of the ions in solution, and now we do have to pay attention to the volume of this. The total volume of this is 0.0600 liters. So then you have to kind of figure out how much of the stuff is not created, how much is not reacted, and from that you can figure out what your concentrations of the ions are, and then you can throw those back and divide them by the total volume of solution and get your concentration of iron to be 0.015 molar and your concentration of sulfate to also be 0.015 molar. This then becomes a problem like the ones that we've done previously, where you have to consider the KSP expressions and then find the other substances. So if we know what our concentrations of sulfate and iron are, we can plug them into the KSP expressions here for iron hydroxide and solve out what the hydroxide should be. And down here, we can plug in the, we know what the sulfate concentration is, so we can plug in and solve out for the sulfate if we know what the barium concentration is, rather.